All right, keep going here. So last class we left off on kind of talking about linear regression, interpreting coefficient results that we see. I'll go through some more Excel examples today because of the mishap last class. I figured out I had to turn off kind of OneDrive for some reason that blocks the add-ins. So we left off with this example where we had this y variable, which was the income of an individual, x variable, which was the number of days to kind of use marijuana each month. And we said the way we can interpret this coefficient is if they use marijuana one more day a month, we expect that their y variable or income goes down by whatever that coefficient estimate is. Now we have to remember these coefficients are estimates, right? They're coming from data. We're using data, right? Go through every observation. And so we have actual data that these are just estimates from a sample. And so we need to be able to say, well, can I say with certainty that this relationship between the x and y variable exists? Right? So we always started out assuming that the slope coefficient, or b, right, which came from kind of this equation. This is what we were trying to estimate. Right? So we assume that that relationship is zero. There's no relationship between these two variables. If we can find enough evidence that shows that the coefficient or the estimate is, positive or negative, something other than zero, well, is it enough evidence, right? Is it far enough away from this assumed true value? We want to think about, we're really finding kind of like coefficient estimates, so we call that b hat. We're assuming that the true relationship is zero. If we find something that's not zero, is it far enough away from that assumed true value such that we can reject? Well, we're always doing a two-tailed test, so whatever value we find, it was equally as likely for us to see something on the other side. And so we get our total p-value, and then it just comes back down to, well, we can reject if that p-value is less than alpha. Right? So what are we rejecting? We're rejecting that there is no relationship. We're saying that we found significant evidence that there is a relationship between this x and y variable. Okay? Kind of a quick little recap. So, once we have that output from Excel, right, it gives us a test statistic. It gives us the p-value that's derived from that test statistic. Notice here it's very, very small, pretty much zero. And the way that it comes up with that test statistic is we're always using that assumed true value of zero. So it's really just whatever the coefficient estimate is divided by the standard error. And the standard error is some measure of the mistakes we're making, right? It's going through every observation. It's taking the actual y value, subtract the predicted y value that you would get if you use these estimates, kind of squaring them to overpenalize like really bad mistakes, and then kind of adding them all up, right? And then you don't have to worry too much about this denominator, but kind of thinking about this is similar to like a sample variance, but we now have two kind of pieces of data, right? Two variables as opposed to one, so n-2 instead of n-1, okay? So if we think about, right, and how we come up with this test statistic, you could actually just go through. It's the coefficient divided by the standard error. We don't have to look up the p. I'm not going to make you look these p-values up. We'd have, talking about degrees of freedom would be a whole nother conversation. So all we have to think about is if I say didn't have this, but all I was given was the coefficients and standard errors, could I come up with the test statistics? Well, let's say instead the y variable we're interested in is birth weight. And the b variable is just this variable of 1 if the mother smoked while pregnant, 0 if not. Right? So when you think about this coefficient, right, we estimate it to be negative 213. Right? We've got a standard error on that estimate of what, approximately 50. So if I'm just trying to kind of guesstimate where this test statistic is going to be near, well, if I take the coefficient divided by the standard error, that will be my test statistic. So about negative 200 divided by about 50. 50 goes into 200 about 4 times. Our coefficient's negative, so about negative 4. If I actually kind of do the math, 213.23 divided by 48.92, I'll get something near 4, but right, it's going to be a little bit different. It ends up being negative 4.36. Right? So that's how we would calculate test statistics if all we were given was kind of this coefficient estimate and the standard errors. But we know in practice, right, Excel will give us this additional, the test statistic, the p-value. And so, we don't really have to do this in practice, but it's good to know where that test statistic is coming from, okay? How would I interpret this coefficient? This one's a little bit different than examples we've looked at. So the way I have kind of said it before in general, it's always a 1 unit increase in my x variable causes the predicted y variable to go up or down by whatever the coefficient is, right? And we kind of had a nice visual on the graph of that, right? If I was to draw a line and think about moving over 1 unit of x, the slope of that line tells me how much y will go up or down. So here I've got negative 213. So what's a 1 unit increase here? Well, this smoking variable was just a 1. The mother smokes while she's pregnant, 0 if not. So a 1 unit increase is really just going from, if a mother goes from not smoking to smoking while pregnant, the predicted weight of the child goes down by about 213 grams. We have this in grams, I think. I'm not sure yeah, right here, right? 213 grams. So the interpretation is still 1 unit. It's just if we have this binary variable, that's 0, 1, a 1 unit increase is just going from 0 to 1, right? The group that was identified with the 0 to belonging to the group that was identified with a 1. And we'll get a few more examples of this today. We'll get some kind of practice with some other binary variables. Okay? So that's kind of where we left off, right? We were just looking at the relationship between kind of 2 variables, right? X and Y. Well, we know that like a child's birth weight is impacted by a lot of other things other than just whether or not the mother smoked while pregnant. We know that your income is definitely based on a lot of other things, right? Other than just how much marijuana you smoke each month. And so what we want to do is move on to not just simple linear regression, where we have kind of this nice just linear line where we only have to estimate, right, the slope of that line, b. We might have a lot of other things that matter as well. So maybe it's, we call this b1 and x1. Maybe there's another variable that we also know impacts income. Right? So we want to include that into the regression. Right? So, we'll call that multiple regression, where we can add in more independent variables or more x variables or more right-hand side variables. Right? All the kind of the same terminology for those variables on the right. Okay, so here I've wrote it as beta. We'll see this kind of a lot. You can think about it as every time I've been using b up to this point, we really can just replace that with beta. It's just a different way to notationally, yeah, I guess that's right, identify what that slope is, right? What that slope coefficient is. So here we would have beta 0. Well, that's our intercept or our constant. That's where kind of this variable starts if all other variables in this equation are equal to 0. We then start adding in, well, maybe what's the impact of education on income? What's the effect of age on income? Right? We start adding in these additional variables. And we know that if we were to make predictions, even after we get these coefficient estimates, the actual y value will still incorporate that error term that's specific to that individual, right? And we're not kind of able to observe this until we make our prediction and then look at what the actual y value is. So we could think about how crime in a county might be affected by a lot of other things, right? Police expenditures, you can kind of think about how much they're spending on their police force, the number of police, maybe what the unemployment rate is in the area. There's a lot of other factors that can matter. So let's say I had crime rates as my y variable, and I just looked at police expenditures as my x variable. So I start out thinking about, I want to estimate this equation where I've got what? Crime is a function of police expenditures, right? How much they're spending on their police force. What do you think the sign of this slope should be? If I think about the relationship between crime and police expenditures, if I spend more on my police force, what do you think would happen to crime? You think it would go down, right? I mean, that makes a lot of sense. Like, that's the actual causal relationship we could think about. The problem is, this is not telling you the causal relationship. We're trying to get closer to the causal relationship. When we first start out with a simple linear regression, it's just evidence of correlation. So if we're not thinking about the causal relationship, what is the correlation of these variables? Well, areas that maybe aren't as nice, maybe are more likely to have crime, what do they have to do? They have to spend more money on their police force, right? And so it could just be that in areas where unemployment rates are high, there's not a lot of high-paying jobs, it's high population, it may be that they have to spend more money on their police force because all these other things are causing high crime rates, right? But those aren't part of the picture, right? We haven't included those into our regression. Right? So actually, if I run this regression, what I'm actually going to find is that that coefficient is actually positive, right? Because it's picking up all these other things that are correlated with police expenditures, all these other things that cause crime to be high, which is why I have to spend more money on my police force. Right? So if I don't control for those things, right? If I'm not comparing two counties that look the same demographic-wise, like age, and when I say demographics, age, everything, right? That don't look the same kind of income, like socioeconomic-wise, that don't look the same on, unemployment-wise, like area of the country, all these things, then, who knows what I'm going to get here. What I ideally want to do is be able to compare two counties that look the same on every other measure. It's just that one of them is spending more on their police force. And then we could get at that causal relationship, which we kind of intuitively know is likely not what we're seeing from our coefficient estimate. So how can we do that? How can we control for these other things? You can start adding them in as additional variables. So let's say I just add in 1, which is the unemployment rate. Right? So the unemployment rate is trying to somewhat capture kind of the socioeconomic kind of level of that county, as well as maybe job opportunities, right? We know that kind of crime and kind of unemployment are highly correlated. If people don't have a job and they need money, they're more likely to go try to steal to get money to survive. And so if I start adding in more variables, it may be that I get a better idea of what that actual causal relationship is between crime and police force expenditures, because I'm able to hold constant all these other things. So I might start throwing other variables in there. So why can I now interpret this? What's now the interpretation of this slope coefficient? What's still the effect of spending $1 more on your police force on crime rates, but every other variable that I add in, I now get to say, this is beta 1 is the effect of spending $1 more on my police force on crime rates, holding constant everything else in my regression. Well, that's a lot more powerful, especially if I can start to add in not just the unemployment rate, but maybe the average income, right? Maybe crime rates 10 years prior, right? Trying to hold kind of constant where crime was before this year I started spending money on my police force, right? So we can start to include all these other variables. And now when we add this additional kind of component to the interpretation, which is holding all else constant, well, if we've included a lot of other variables in our estimate, our regression equation, that makes it a lot more powerful, because now I'm comparing almost more apples to apples than I was before. Okay, so we want to start controlling for other things. If we want to think about the math of this, right? Well, I'm still minimizing the sum of my squared errors. Don't worry about writing this down. So now when I substitute in my prediction, I've got a bunch more kind of estimates I'm trying to come up with. I'm not only trying to come up with the kind of estimate for B1, but also B2, B3, all the way up to Bn. Well, I can still do the same process, take a derivative of this function in respect to all these different things, set them equal to 0. Now, instead of having 2 equations, 2 unknowns, I'll have I could have 50 equations, 50 unknowns. Well, that's a lot of math to do by hand, right? Well, we're not going to actually do it by hand. Excel is going to kind of do all that work for us behind the scenes, okay? So, if you really are interested, UC Davis, this professor put up a pretty nice little kind of multiple regression thing. So I just liked it. It was from a textbook, but it's a nice kind of mathematical walkthrough of multiple linear regression. You want to think about it that way. But let's not worry about it. Because the interpretation, once we get these results from Excel, is still the same. We just add in this additional phrase. It seems small, but it's really important if we've held a lot of other things constant. Right? So, as we add in additional variables, right, you can kind of think about, if I'm trying to predict, let's go back to, we can use this one. Well, this one makes a little more sense. So if I'm trying to predict income, and all I have is, what was that? Kind of that marijuana variable. I'm probably not going to be able to, just using this data, come up with a really good prediction of income, right? But if I start adding in things like education, and maybe age, and maybe region of the country, well, now I'm able to, I have more information about this individual. It's likely that I'm going to be able to come up with a more accurate prediction about what their income is going to be, right? For instance, even if I had like maybe, I don't know what their job title was, right? So as I add in more of these variables, I'm able to get a better prediction about what this Y variable is. Right? And that just makes sense. I have more information about this person. I can better predict their income. So a measure of that we're going to be able to obtain from Excel, is R squared, right? So R squared kind of measures the percent of the variation that we see in that dependent Y variable that we're trying to predict, the percent of that, the variation we just see in that variable that we're able to explain using all of the variables that we included on that right-hand side, or all those independent X variables, okay? So the highest R squared can get would be what? If it's measuring the percent, the highest percent we could explain would be 100, right? Or kind of in decimal form, we can think about an R squared of 1, right? 100%. Okay. So if we think about how this is kind of obtained, it's just kind of, you don't have to worry about these. You're not doing these by hand, but to kind of give you a little bit of intuition, we're going to take the variation that we see in our predicted Y values for each observation, whatever its predicted Y value is, from the average Y, right? We're going to square that. It's kind of like, based off our predictions, the variation we see in the data from that average Y variable is kind of this SSR, right? Some of the squares from the regression. Total sum of squares would be, well, what is the actual variation that exists in this Y variable? Well, that would be the difference for the actual Y values and that average Y. So basically, think about it as, what's the only thing that Y hat doesn't have that Y does? The only thing that Y hat doesn't have are those epsilon terms, right? Those individual kind of like error terms that we don't know exactly where that's coming from, but it's not coming from the variables that we've included in the regression, right? So our predictions will kind of pick up kind of all the variation that we're able to explain, while this total sum of squares will pick up all of the variation that exists in the data, right? So the ratio of those two, well, that's just the percent of the data that, or the percent of that Y variable that I'm able to explain, okay? So we already talked about this a little bit, but right, we're not actually getting causation. We're really just picking up correlation. When we start adding in additional variables, yeah, we're doing a better job of getting closer to what that correlation or to what that causation is, but it's still evidence of a correlation. We still could be missing things in this regression, right? I still could be missing, maybe age demographics here. I mean, I guess I'm kind of assuming this. I'm not an expert. I'm guessing that old people don't commit crimes at as high of a level as maybe younger people, right? So maybe that matters. Okay? So, you think about for the birth weight one as well. Right? If we start to think about this just as being a correlation and not causation, if I were to estimate birth weight and whether or not the mother smoked, and I find it's negative, which makes sense, right? That was the example we had, 253 fewer grams. Why might the actual relationship not be that high? Maybe the relationship is actually 0. Right? Why could maybe I see this kind of large negative effect that looks like it's coming from a mother smoking while pregnant, when in fact the actual kind of effect is something much closer to 0? What might be one thing that's correlated with, that we don't have in this regression, someone smoking while pregnant? What would you think might be true about that individual? Potentially lower. Do you think that person would be more or less likely to only have a high school degree? Probably more likely, right? Lower levels of education. In fact, if we look at the data, smoking while pregnant is much more prevalent along lower educated individuals than higher educated individuals, and which makes sense. It's also more prevalent among lower income individuals, right? Which having less income, having lower education, not being as likely to know the things you should do kind of to have kind of a healthy pregnancy, or might, not have healthy food sources available to kind of have a healthier pregnancy. Those things are going to negatively impact birth weight. But if I don't include them in this regression and they're correlated with the only thing I've included, well, it's going to kind of pick up the effect of all those other things, right? So right now, when I have this simple linear regression, my slope coefficient isn't just telling me the impact of smoking while pregnant, it's telling me the impact of all the other things that are correlated with smoking while pregnant as well, right? So I've kind of like, without controlling for anything else, it's really hard for me to put too much stock in this, right? So we kind of call this the omitted variable bias, right? When I'm leaving out variables that I should be including, the estimates for those coefficients I see will be biased, right? So, things can go wrong. We're trying to pick these up. I've already kind of explained this, right? These omitted variables Z, we leave them out of the regression and they actually have an important and a very significant impact on that Y variable. Our estimates for the slope coefficient on what we included, these X variables, won't be as reliable. So Z could be causing both X and Y, and if I leave it out of the regression, now it's going to look like X is causing Y. So I saw kind of the good omitted variable bias here, right, is I used to think correlation implied causation. Then I took a statistics class, now I don't. Sounds like the class helped. Well, maybe, right? Because maybe it wasn't the class that was impacting this knowledge. It might be other things correlated with taking that class that I'm not kind of factoring in, right? So let's look at a couple examples of this. So I always thought this was a kind of an interesting little, if I took this data on autism rates from what, 98 to 2008, and organic food sales, I mean, if I estimate a coefficient between these two, it's going to be highly significant and look like it's positive, right? But I am no expert on autism or the effects of organic food on individuals. My guess is there's no causal effect here, right? Organic food sales aren't causing autism rates to go up. What's likely is there's other things that are correlated with these two variables that I'm not entering into the picture, right? It's likely that maybe higher incomes make individuals more likely to go to the doctor. Maybe advances in science have allowed us to identify autism better, have also allowed for us to understand that organic food may be a good substitute to things with pesticides in it, or whatever the kind of missing variables are there, right? So how much will our estimates be biased by? Don't write any of this down. This is just kind of trying to give you a little bit of background, especially if you're kind of mathematically minded, maybe think about this a little bit more, right? So if I try to estimate, get off my screen, there we go. So these stars, we can kind of think about as, I usually write it as like A and B hat. If I try to estimate what this effect is from this X variable on this Y variable, if I were to run this regression, I am able to observe this slope coefficient B star, or like I said, I usually call it B hat. It'll pick up what the actual effect is, right? Kind of think about it as like the population effect, right? I only have a kind of sample effect, or an estimate, but it also picks up this additional component, right? It's bias, because it picks up this correlation that X would have with other variables, call them X2, that I didn't include in the regression. This was the idea that smoking variable, it told me the effects of smoking while pregnant on the birth weight, but it also was picking up the effects of lower income, lower education levels, right? And so when those variable you included in the regression is correlated with variables that matter, that are left out of the regression, you pick up this additional bias component. Right? And we might revisit this a little bit more after today, but for now, just kind of know that that effect is there, right? And you can walk through the math of it, of why that would be the case. But for now, let's just assume that we know that exists, right? So how can I eliminate this bias? Well, if I include X2 in the regression, I get rid of this. Right? But you can imagine, if I don't think about just one other variable, if I think about there's like 50 other variables, so there'd be like 50 other additional bias components here. The only way I can get rid of them is if I include them in my regression. Right? So we'll walk through an example here. So I think I have the results in the slide. I'm going to walk through it in Excel. Oh, stop it. All right. So zoom in a little bit here so you can see what we're doing a little bit better. So here's that GPA data set. It's in the in-class data folder on Canvas. I've got individuals' GPA, their SAT score, whether or not they're an athlete, so kind of whether or not they're a student athlete, verbal math score, some tests I took, high school rank, et cetera, et cetera. Right? So I'm just going to first say, okay, I want to understand, I might think you have some preconceived notions of athletes and kind of maybe their ability levels, right? Their intelligence levels. But I also have to realize, like, maybe the effect of being an athlete, like, gives me some really good time management skills, some leadership qualities, potentially. It also, though, detracts from the amount of time I have to devote to my studies. And so I'm not really sure what the effect of being a student athlete is. Right? So I'm going to go to data, right? It's this data analysis tab that once we download it once, it should always be there. So I'll click that data analysis tab. I'll scroll down here, and there's this regression option, right? So I click on the regression option, hit OK. What's my Y variable here? Well, I'm thinking about, I want to be able to predict somebody's GPA. So I'll select that GPA, kind of start at the first, control shift down arrow. If you try to select the whole column, it's not a good idea to do that. I'm going to make sure that we kind of are selecting just down to the end of the data. Okay? Hit this little arrow again. Hit this next arrow. I want to select my Y variable. I clicked on a cell, so now it didn't send me to the top. So I want to look at this athlete variable, right? How does that kind of, what effect does being a student athlete have on my GPA? So I control shift, or command shift on a Mac, select that entire variable, right? I selected the very first row that had the labels on it, and hopefully I'll remember by the end of the class. I'll show you what happens if we don't select the labels. I'll put it on a new worksheet. It's the only thing I should have to select. Make sure that these boxes aren't selected. I'll hit OK. Right. So let's get a little bit bigger view here. And we can see that it looks like the effect of being an athlete. So this is another 0, 1 variable, right? So the interpretation of this coefficient is this is the effect of going from not being a student athlete to being a student athlete on your GPA, right? So it would predict that if I'm a student athlete, the effect that would have on my GPA, I would have about, what, 0.28 GPA lower, which is a pretty sizable effect if you're talking about something from a 0 to 4 scale. Right? Now, the p-value, remember, e to the negative, that's essentially 0. That's move the decimal points 9 places to the left. So this is very, very small, so I can reject that null, which is that there's no effect. I found significant evidence of there being an effect of being a student athlete on college GPA. Now, another thing just to kind of mention here, notice our R squared. What percent of the data are we explaining? Well, the R squared, we can think of it as a percentage, but it's going to be kind of in decimal form. So 0.008 would be, we're only explaining 0.8% of the variation that exists in GPA. So just being, whether or not someone's a student athlete doesn't allow you to make a very good prediction. There's still like 99% of the variation we see in GPA unaccounted for from our simple linear regression. Right? Well, if we want to get a slightly better kind of maybe prediction on someone's GPA, we probably don't want to know whether or not they're an athlete. We kind of even talked about last class, SAT is a pretty good predictor, right? It's not perfect. There's flaws with it for sure, but we could use maybe the verbal math score that they had as well. Both these things are some measure of innate intellectual ability, which you would think is something that would highly impact college GPAs, right? Your innate kind of intellectual inability, or not inability, ability, right? So we go to data, we go to data analysis, regression, hit OK. So we're going to keep that Y variable the same, right? But now we're going to want to select the SAT score and the athlete variable. So you just click on SAT, hold that click, go over, Control Shift, hit the down arrow. Notice it's selected now both of these variables, right? I'll then go back. Everything's still set up okay. I hit OK. Now I've got this new output. And when I start looking at that, how has that impacted, including that additional variable, how has that impacted the estimate I have for being a student athlete on GPAs? Well, now remember the interpretation of that coefficient on athlete is this is the effect of being a student athlete on the college GPA, holding constant everything else. So really the thought experiment is like if I were to take two individuals now with the same SAT score, but one of them is a student athlete and the other one isn't, what is the effect of being a student athlete on that other person's GPA, college GPA? So holding these other things constant, the thought experiment is like I'm now comparing two people with the same SAT score, which is much better, right? Because if I don't have that information, like if I'm just thinking about that variable of a student athlete, I mean, that student athlete might have a lower, kind of innate intellectual ability or vice versa, right? So now when I look at this, I say, well, now the effect of being a student athlete looks like it's only going to decrease the GPA by about 0.05. And in fact, if I look at the p-value at 0.26, at the 90% level, can I reject the null hypothesis? Well, at the 90% level, alpha is 0.1. My p-value is not less than 0.1. So at the 90% level, I can't even say that being a student athlete has any effect on GPAs, right? I'll still get a slope coefficient here, but it's kind of like when we talked about, if I see a difference that isn't zero, well, just because we have this assumed true difference of zero, if I see something that's far away, like that's kind of a little bit away from it, that's still fairly likely if the true difference was zero. So even if the true effect was zero of being an athlete on GPAs, it's still likely based off of our sample size that we could, and the kind of variation of the data, that we could see this estimate, even if the true effect or kind of the true correlation was zero. So just by adding in one variable, we went from saying, geez, you should advise all students, don't be a student athlete, it'll hurt your GPA, to just controlling for some proxy even, not even their actual, but some proxy of their intellectual ability, holding that constant, being a student athlete, we can't say has any impact on their GPA. Right? So this is a really good example of the omitted variable bias. Also notice our R squared. It went from 0.008 to almost 0.17. So we're able to explain about 16% more of the variation in GPA just with knowing the individual's SAT score, right? So we would kind of say that this regression model that includes not just kind of one X variable, but two here, is a much better predictor of the student's GPA, right? So you can compare those R squareds across these different models. When I say models, right, they're kind of different linear regressions. 0.008, we're barely explaining any of the variation. Just including the SAT score, we're explaining quite a bit more. Now, we're still not explaining like 83% of the variation, so we still have some work to do. But if we go back to that original data on sheet 1, let's start including a bunch of other things. So I'm not going to use this today. Everything else we should be able to use. Yeah, so let's go to data analysis, regression. Now for my X variable, my right-hand side, let's just include everything we have here except for this SAT score squared variable. I doubt we're not going to get there today, but maybe next class or Friday we'll talk about kind of doing something like that. So Control Shift or Command Shift, hit the down arrow. We've selected every variable now for our regression. We'll hit OK. We now look at the output. So you can kind of think about this here. I now have a coefficient estimate for the relationship between high school size and GPA, holding all this other stuff constant. I have an estimate for the relationship between total credit hours taken and college GPA, holding everything else constant, so on and so forth. Right? So now when I look at this athlete variable, once I control for all these other factors, now what's the effect of being a student athlete on GPA? It's pretty high. So it actually has a positive effect now of about 0.18. And the p-value is essentially 0, so I can say it's a significant effect, right? I can reject the null. I found strong evidence it's a significant effect, right? Even at the 99% level, or at the 1% significance level of being a student athlete on college GPAs, right? So just by including these additional control variables, starting out from that simple linear regression, I went from thinking it's a terrible thing for someone to be a student athlete to actually seeing being a student athlete has a pretty positive effect on your GPAs. Because, and this is a more strong statement because I'm not only saying it's a positive relationship, I'm saying holding constant So the thought experiment here is, holding constant everything else is, if I was looking at two individuals with the same SAT score, same score on this verbal math test they took, same high school rank, they're both either male or both female, their race is the same, they have the same number of credit hours, their high school size was the same, but one of them was a student athlete, one of them wasn't, that student athlete would have a GPA of about 0.17 higher. And that's a lot more powerful of a statement, right? I'm saying, these two individuals that otherwise look almost identical, it's just that one of the student athlete has that much higher of a GPA, okay? Any questions on that? Anything that I did kind of moving from the very first simple linear regression to kind of moving forward? We're okay with this? So, this is kind of shows the importance of kind of, the omitted variable bias when we don't include variables into our regression that do in fact matter or have an effect on our Y variable. We have to always keep in mind, these are just correlation estimates, not causal. And you'll also notice we have a pretty, so what is the P? Okay, I'll talk about it in a second. You'll also notice the R squared when we include these additional variables, we're now up to about 30% of the variation explained. So that's good, but I mean, there's still 70% out there that we can't explain, right? So there's probably a lot of other omitted variables that are out there that matter that we haven't been able to capture, right? So we still should be a little bit cautious interpreting these results. So what does the high p-value on the intercept mean? We're thinking about kind of, how to explain a real significant intercept. So the intercept is just, you're trying to pinpoint down, this is a good point. So if I have this GPA variable, and I'm trying to predict it, right? I have my estimate for A, what was it? We have athlete, we have, and that's the estimate, we have the estimate on SAT score, and every other variable in this equation, right? Well, once I have numbers for all these things, I could come up with a prediction for any one individual by just saying, okay, is the student an athlete or not? If they were, put a 1 in here. If not, put a 0. Plug in that student's SAT score, plug in their values for every other variable, and I could come up with what their predicted GPA is. Okay? The interpretation of our intercept, remember when we just had one variable, the interpretation of the intercept was, well, if x is equal to 0, the intercept or the constant is just kind of what the predicted y value would be. Like that's where it kind of starts out at when x is equal to 0. Well, now the interpretation is this is the predicted value for our y variable when every other variable is equal to 0. Because now 0 times anything, any coefficient, is 0. So if every other variable is 0, all we're left with is that intercept, right? So saying that it's highly significant is just telling you that this GPA has kind of an initial starting point that's not impacted by anything that you've included in the regression, right? And if it wasn't 0, like, I mean, I guess if we want to think about here in this particular example, what that's saying is if we had a very low, high p-value that made this so that we couldn't say that the constant or the intercept was anything different than 0, that would mean that no matter what we had on the right-hand side for these variables, if you showed up and just put the effort in and like submitted things, that you couldn't get anything other than an F, right? Your GPA would be 0, right? Well, we know that's probably not true. Most people, no matter what these other kind of variables are, they're probably able to obtain some positive GPA. So my guess is if we look at this, could be wrong, but right, yeah, like 0.92, right? It's some positive amount with a pretty significant amount, right? Even if someone is, has some of these things that are negative, right? Even if they are in all those categories, they're still likely to start out with some kind of initial starting GPA there. Right? Hopefully that answers it. I think that was kind of what you're asking. What is the p-value? Yeah, it just means, so we think about our assumption for, since I'm using A and B here, it's the same as my slope coefficients. I'm assuming that the intercept is 0. So if I find a pretty low p-value and I can reject the null for the intercept, what I'm saying is I can reject that the intercept is 0. I found significant evidence that it's something other than 0, in this case, 0.92. All right. So this is a pretty good omitted variable bias example. Kind of fun little data set to play around with as well. What do we got? What, 9 minutes? Okay, so I'll show you a couple things in Excel just to like avoid. So the individual assignment has you kind of run some regressions with your own data. So I'll show you some pitfalls that can exist, right? So let's go back to this sheet 1. That was kind of my original data. And also I'm doing a terrible job today of management. I probably every single time should be like labeling these, right? So all variables, SAT and athlete, and then kind of athlete, so I can navigate these a little bit better. And this one will go kind of raw data. Okay. So let's say I want to use a model. So go back to this regression. And I only want to select the SAT score variable, so I'll hit Control-Shift down arrow. But then I also want to include one of these other ones. Let's say high school rank. So I hold Control, click on high school rank. I'm holding Control so I can select multiple columns. Hold the Shift again, go down. So now I just want these two X variables, right? And I've got my original Y variable, which is still GPA in that A column. If I hit OK here, it's going to give me this error term, right? So it says they're not contiguous. So what that means is Excel's mad at me because the only way that it can do this linear regression is if these cells are next to each other, right? So if that's the case, unfortunately, all I have to do is I can select these columns, and I'll just move them next to each other. And now, when I go here, I just have to make sure that these two variables that I wanted are next to each other. Now, when I select both of them, hit OK, it'll run it, right? So it just needs the columns to be next to each other. So if you have a data set with additional variables that you don't need, you might have a little bit of like data kind of, I guess, cleaning to do, right? Moving the columns so that they're all next to each other. Right? Another issue that you can have, and this very well, the number of you that there are, and me trying to get them out to you quickly, there's likely one of your data sets that might have this issue, right? So let's say, there's a lot of observations here. So let's say way down here, there's a missing value, right, for whatever reason. Okay? If I go and try to run this regression now, I think hopefully I put the missing value in the right variable. It's going to get mad at me. It's going to give me this lin estimate. So what that is basically saying is, you told me to use two variables, but one of them has fewer observations than the other, right? There was a missing observation, and Excel doesn't know how to deal with that. Right? So if that's the case, an easy way to kind of troubleshoot this is, typically, especially when it comes to like regression, you have this original data set in your raw data file. So I'm just going to select all the data. So I did there was go to that first one, you go Control-Shift, hit over, and then down, selects my entire data set. Go to Data, Filter. Okay. I'm going to go back up to the top here. So what I can do now is I can inspect every variable. So if I inspect SAT score, I can filter it out so that it only shows me people that, I don't know, had a 500, right? So I could do that. Now the old data still exists. Notice it's just like hiding it. It's only showing you these two rows. So I can then go to kind of select all, selects every single one again. Now I'm seeing all my data. But notice this didn't have, if I go scroll down here, it has all numerical values. So that's good. If I'm missing one, and I scroll down for this high school rank, notice it tells me there's some blanks. Right? So what I might want to do is go down here, select that blanks. Now it shows me, oh yeah, that's why it wasn't running. I had this bad observation. Now this isn't what you should do kind of in practice necessarily, right? This is not, we can't use, if high school rank is a variable that we want to use, we can't do that here, right? So typically, if I was missing some data, I might delete this row. But before I do that, I always want to keep my raw data, because if maybe I want to do something else where I don't need that variable. So I'm going to go on another sheet. I would paste it. Right? Now I'll go to filter this. Look at that variable. Oops, and just deselect all. Scroll down. I know that there's a blank. Now I'll delete this. And actually, I'll right-click on the row and just hit delete row. Now I want to be able to see all the data again, so I'll select all. Now, when I go to that regression tool, now when I want to select these two guys, and I think I'm going to have to reselect this because it was kind of the cell references coming from my other sheet. So I select GPA. Now I can actually get that regression ran, right? But I don't just want to like start deleting the observations. I want to keep that raw data set intact in case there are other cases where I don't need that one variable. I still have, that it's not like the observation was completely worthless. It had a lot of other information that I could use to make some predictions. I just couldn't run the particular regression I wanted to because it had missing values there. Okay. Does that make sense? How you would go about that? And if you're running into any issues with that LinS and the data sets that I sent you, let me know. Because some of them, it might have just been a matter of, it's sometimes easier for me to clean it up in a different program where like if there's some missing values, I sometimes forget that in Excel, it doesn't treat them. So sometimes when I had an original data set, it's not that they're missing values, they might have been zeros. And so then when I moved it over to Excel, they just show up as blanks. So let me know if you're kind of running into any problems with your individual data sets. I think I probably, like I said, I think they should all be okay, but with the number of you that there are, the probability I made a mistake is not likely zero. So it should give us a pretty good start at kind of working on those assignments, kind of understanding the omitted variable bias. Next class, we'll kind of keep moving through some examples. I'll ask you next class what are some maybe examples you want to see. We might actually look at like an academic paper and kind of how they did some regression. But we'll keep talking through some more issues that we have with doing linear regression and just kind of continue to plug away at that. All right. I will see you guys on Wednesday.